together during dinner, and I told him, I said, I really admired the fact that he was so much in love with his wife that he still called her dear and honey. And he very slowly looked over to me and he said, son, I don't want to disillusion you, but I forgot her name 11 years ago. That's my Valentine's story. Anyway, I'm here to talk about primarily our catalyst for selective catalytic reduction. DeNOx is a very hot topic in Texas right now. The TNRCC has mandated that essentially everything that has a flue will reduce NOx by 90% by the year 2007, and a plan has to be in place to do so by the year 2004. And this is an extension, of course, of what's happened in California, and it's going to be everywhere sooner or later. So I think it's a reasonable topic. Of course, the power industry has been dealing with this for years, and if you looked at Haldor Topsoe's sales in DeNOx catalyst, probably 90% of it is in the power industry right now. But there are 3,000 heaters alone in Houston that will need selective catalytic reduction units. And low NOx burners aren't going to get it. They'll get you close, but they won't get you all the way to where the mandate will take you. We think that low NOx burners are still a good idea because, as you'll see, it at least lowers the amount of ammonia you have to use and cut your operating costs, and it's a relatively low expenditure to make. And I'm not here to sell John Zink, but it's a reality that when most people look at DeNOx systems, they look at either or. And in reality, we should be looking at it as both. So let's start. As an agenda, I'm going to spend a little time introducing Haldor Topsoe for a couple of reasons. Number one, I represent Haldor Topsoe. Number two, I don't know how familiar most of you people are with the company, so I want to make sure that you are familiar with it by the time we leave. Number two, the sales pitch is inversely proportional to the honorarium, and there isn't an honorarium, so you get a hell of a sales pitch. I will spend as little time as possible on that to get down to the meat of what we're going to talk about, which is environmental technology in general, DeNOx technology specifically, and within that category, DeNOx catalyst. I'll talk a little bit about the operating conditions, physical and chemical features of systems, the production of the catalyst, module design using the catalyst, hydraulic diameter and how important that is in selecting the right catalyst for an SCR, the DeNOx reaction mechanism, activity and deactivation, what causes deactivation, catalyst design, and I'll go through the references for our company and the guarantees that we offer should you select, or should anyone select Topsoe as the provider of your SCR. Oh, normally with a larger group I would say, well, hold all your questions till the end, but I really would prefer a dialogue. So as we go through this, I think it's probably more productive that stop me and anything we want to talk about or is on your mind, let's talk about it. This gentleman is Dr. Haldor Topsoe, who founded the company in 1940. His philosophy, second to none. I always get a kick out of that because I always think of a middleweight fighter about 10 years ago named Michael Nunn. And I remember he had a robe that said Michael second to none. I was thinking it was spelled N-U-N-N, but I thought it was a cute nickname. But he means it. Dr. Topsoe is 87 years old and still runs the company. He skied in San Moritz this winter with his wife, who was 86, and they celebrated their 65th wedding anniversary last Wednesday. His son Henrik is hoping to take over someday. I think Henrik's 64. Deep commitment to R&D. Maybe one of the few companies left in the world that still puts 20% of its gross into research and development. About half the people in the company work in the R&D group, to give you an idea. We do two things. We sell catalyst and we sell technology to utilize those catalysts. And a lot of people in the catalyst group will tell you that the only reason we sell technology is so we can sell catalyst. And since I run the technology sales group, I have a hard time with that. It's, in reality, basically true. Oops. What happened here?
You know how to make that pull?
Start over. I hit the wrong button, my fault. This is what, in selling catalyst and technology, we are involved in catalyst manufacture in 2 locations, process licensing, process engineering, critical equipment design, and the best way I can categorize that is we sell hydrogen technology and we make sure the reformer is built correctly, so we get involved in that. But otherwise, we are not an engineering construction company. We do have a fab shop and we make specialized equipment, for example, CADOX units. We're involved in fuel cell development right now. I would say it tends towards those things that can be skid mounted. And that division is in Denmark. Our head office is a campus in Lyngby, Denmark, north of Copenhagen, where there are 1,500 employees, as I said, about half of which are involved in research and development. Offices around the world, but the main offices that have engineering and technology capability are Copenhagen, Houston, and Los Angeles. Those of you who may be involved in the hydro treating or hydro processing end of the refining business may know our group in Anaheim. It's the old Unical. There are 9 of them out there. I think they've got a total of about 200 years experience in hydro processing. We're selling essentially hydro treating and hydro cracking, grading, internals, and catalyst. We're involved in fundamental research, surface science, kinetics, bench scale units, and pilot units. This picture is a pilot unit in Houston, which is associated with our catalyst manufacturing plant. On the right there is an allothermal reformer. On the left is an SMR, and towards the back, a new technology we're developing for small hydrogen plants. It's called convection reforming, which is suitable for hydrogen plants up to about 10, 15 million standard cubic foot a day. We do a lot of operational testing. In the case of our DeNOx catalyst, it's in duct. We do a lot of side stream, and we'll put together full cassettes to test specific gas properties. And this picture is a picture of one of the modules. We'll get into that more later. In Houston, we are now tripling the size of our DeNOx catalyst manufacturing facility in anticipation of everyone getting to 2004 and being in a hurry to put in SCRs. There is not enough DeNOx catalyst right now to satisfy the needs of Texas, let alone the rest of the country. There are only two DeNOx catalyst manufacturers in the United States. So I expect that the people that act quickly will be better off than the ones that wait in Texas until 2007.
If you don't mind,
picture of our plant.
do you mind if I ask who the other manufacturer is?
Criterion.
Okay.
Technologies that we are involved in the environment include DeNOx, which is the removal of nitrogen oxides, what we call WSA, which stands for wet gas sulfuric acid, and essentially it's a sulfur management system for a refinery. In reality, it works best when that refinery has a sulfuric acid alkylation unit, because what a WSA plant will do is take all the SO2 off the Claas units, all the H2S from the amine treaters, and all the spent sulfuric from a sulfuric acid alkylation unit, and make 99% sulfuric acid, out of all of it, with about 100 part per million SO2 going out the stack. So it's a neat little process. SNOx is kind of the combination of the top two, and is applicable more to utility boilers than anything else. It's the removal of SO2 and NOx. We have a CADOX and ReginoX process that removes VOCs, and our newest process in this area to produce ammonium thiosulfate, which is very valuable as a fertilizer and is essentially a refinery process in that it works with the sour gas, or the sour stripper effluent, from which you can make a valuable product. And we have one of these units running right now in Statoil, and we expect this to be a good process to sell in the future.
Is that something you're gonna talk about tonight, Mike, or is that something?
No,
Okay.
I can. What do I do here? Well, what's happening is every once in a while,
Let me do something for you that may help.
It's not in the slideshow mode
Yeah,
either.
put it in the slideshow mode, that may help. You got a mouse?
that's Cleveland, January.
I think you should just hit enter and backspace if you wanna go enter and backspace to go backwards.
Okay, all right. This is gonna do it one thing at a time. I was trying to go a little quicker through this.
Well, I'm sorry.
That's all right, that's all right, I can do this.
It's just, that may make it easier to,
Okay, we kind of skipped this. This was,
oh, no. You got it on
Oh,
automatic.
way to go, Jim.
I screwed up.
how do we get it off of it?
Hit escape, escape. Up in the top left, top left. You can go back, I don't like that.
All right, I'd rather go this way because I want to go through the, we did go by this slide and it indicates the other processes that we're involved in. You'll notice that they're mostly syngas processes or those based on syngas. We have 50% of the ammonia capacity in the world as Topsoe's technology. 25% of the hydrogen technology in the world is Topsoe's. We're involved in synthesis gas production. Right now we're looking at a lot of things for gas to liquids, particularly large production units for dimethyl ether and methanol. Sulfuric gases, we talked about hydroprocessing and the environmental processes. Not mentioned in here, and I promised that I would say a little bit about this, is our, let's call it nascent alkylation technology. And this may be a good time to talk a little bit about that. We call it fixed bed alkylation. It is nothing like the existing processes of sulfuric and HF in that it is plug flow, ambient, basically ambient temperature, low pressure, in a simple reactor. It's a liquid, which is an acid called triflic acid, occluded to a solid. And the beauty of it is that the triflic acid is a reactant and a catalyst that reproduces itself. So that the olefins that go into the reactor react with the triflic to make an ester, which lasts a nanosecond, reacts with an isoparaffin molecule, makes a molecule of alkylate and a molecule of triflic, which plates back out on the solid. And it has a tremendous affinity for this solid, so it stays in the reactor. The reason we don't talk about it much anymore is because we've had two failed attempts at commercialization, one with Amoco and one with Chevron, both of which failed through no fault of the process, but because the, let's say, the haste to a new alkylation process has been removed. The folks that sell the HF process have managed to sell the refiners on the fact that mitigation will take care of the danger, and the government facilities have bought it. So there seems to be no need at this point for a new process that is not less costly than either one of the aforementioned. And that's the problem that we face right now. So I didn't want to spend a lot of time on it, but I wanted to at least tell you where we are on that. And if any of you know Jim Wick, tell him that. All right, we talked about the offices. Let's move right on to technology. Okay. General layout of an SCR, and let's face it, in most of these cases we're going to be talking about retrofit, so I'm going to speak from a retrofit standpoint, where we know the gas decomposition, we know the unit, we know the physical properties of the unit, and we're just looking, all right, how do we get it in here as economically as possible? What it consists of is an ammonia storage tank And this doesn't have to be aqueous or anhydrous. Matter of fact, it can be urea. The ammonia, if it's liquid, is put through an evaporator. I don't have a pointer with me. Let me suffice to do this. The ammonia tank, evaporated, is injected into a stream of the flue gas before going into the SCR, mixed thoroughly, reacted with the NOx to make water and nitrogen. Usually, the ammonia injection system, the evaporator, the storage tank, is on a skid, which is ground level. Normally, there are soot blowers in any facility that has high ash content or high organic content. This would be certainly any boiler, and certainly any cat cracker. If it's clean gas, soot blowers can be eliminated. The SCR reactor and catalyst tends to be a thin plenum in the flue, placed where the temperature is right for the reaction and where there's enough room for good mixing. Almost every SCR I've ever seen has two layers where you're making sure you get all the NOx you can.
How does the system like work with electrostatic precipitators, or the need for electrostatic precipitators?
Usually downstream of the ESP, if you talk about a cat cracker, for example, it turns out the ideal temperature, and I'm going to get into that, for an SCR is exactly downstream of the ESP. The difficulty being that a lot of the older cat crackers, the ESP is very close to the stack, and you're either forced to move the stack or take some other method. Also, with an ESP, you've brought the pressure down to where there isn't much pressure coming out of the back end of the ESP, so you need an ID fan to jump the pressure up before you go into the SCR. So it's a difficult retrofit, but downstream the ESP is the right place to put it. And you want as much dust out of there as possible, so that works out.
You know, it replaces, you don't need a soot blower, but you still need an ESP.
Yes. Now, if you don't have an ESP, you need to get one. Putting a soot blower in there isn't going to do the same job. And I'm going to get into pitch and hydraulic diameter. An FCC in a refinery setting is the worst case scenario for an SCR as far as the soot coming out the back end. But with an ESP, you can design the pitch so that you don't have to replace the catalyst anymore every other 5 years or so. So you can do it on a normal turnaround schedule rather than sooner. What do we do? As I said before, we are not an engineering construction company. We act as a process licensor. We'll do a basic engineering package for the entire unit. We'll do the reactor design. We will supply the ammonia injection system as a skid. We'll do the control analysis system. We'll do the flow model for the gas. We'll provide the ammonia storage, or if you want us to, we'll go find an engineering contractor and we'll take the responsibility for the whole thing on a turnkey basis. Now, we won't do that for utility boiler. There's just too much involved. The catalyst sale alone, for example, Allegheny Power, we just made an $11 million DeNOx catalyst sale to them. The catalyst sale alone is large for our size of company. So we're not about to take on the responsibility for the entire engineering. We'll just sell a catalyst. In a refinery setting, most SCR retrofits are going to be $1 million to $3 million total installed cost. We will take the responsibility for that. Just to point out here while we're on the slide, this is when I said about a double layer of SCR, that's what I meant. They're on frames with static mixers in between, and I'll get into why that's important. But almost all of them are at least 2 layers of catalyst. Ideal operating conditions are one thing, maximum operating conditions are also important. We've dealt with gas flows up to 6 million pounds per hour. That's a utility boiler. NOx contents up to 2,000 parts per million, which you will probably never see in a refinery setting. Maybe so, huh? Temperatures, ideally between 480 degrees and 900 degrees Fahrenheit, and I'll get into a little more why that's important. And pressures up to 45 pounds inlet to the SCR.
What's the minimum, because you mentioned about.
Minimum temperature or minimum pressure?
Pressure.
It's going to be a matter of the pressure drop across the SCR, and that's going to depend on the fluid. You generally need about 5 pounds on the inlet. Otherwise, you're going to need a fan. So everybody in this field, foreign or domestic, has a different kind of corrugated material that they've tried to come up with to affect the porosity of the catalyst. The game here is to make a solid system that has as much surface area as absolutely possible, so that you can bring together a molecule of ammonia, a molecule of oxygen, and a molecule of NOx in the same place on the catalyst at the same time. So turbulent flow is good. Ammonia is a neat issue because you have to have enough there to catalyze, to be involved in the reaction, and not enough so you don't have a large ammonia slip, because there's always going to be a limit of ammonia slip. What is our catalyst? It's a corrugated plate type. I brought a couple here. There are really 8 different pitches that we make, and therefore 8 different hydraulic diameters. These are kind of a very small one and a medium size. I'll just pass them around so you can take a look at what they look like. It's got a very porous structure. It's fiber reinforced. As you can tell, it's very strong. The catalyst itself is titanium dioxide based, and it's impregnated with vanadium pentoxide and a tungsten compound. And it's a very, very secret process. If they let you in a plant, they have to kill you when you walk out. It's because everybody that's in this game right now does things a little bit differently. And I'm going to show you a little bit why ours works better. The production itself involves shaping of the fiberglass carrier at this plant that's shown. That's the Frederiksson, Denmark plant. We've got a similar one in Houston. Wash coating with titanium dioxide, drying, calcination, impregnation with the vanadium and tungsten compounds, calcination again, front edge reinforcement, and then packing in cassettes. And these are the cassettes you see here. They tend to be standard. They're about 2 feet on a square and about 2 feet deep, although they're a little bit longer than 2 feet. They're not exactly a cube. And we put these together to make whatever size we need. It's a picture of the module building blocks. The bottom frame, what we can do here, what we normally do, is assemble this at ground level and lift it into place. In retrofit situations, in some cases we're going to be putting things above an economizer horizontally. It might be vertical, it might be in a slant. So it's got to be a strong casing to hold the modules together. To give you an idea of how we have to do, what we have to do with the flow modeling, we have here shown 6 different catalyst types determined by hydraulic diameter and pitch. And these tend to be to track along equivalently. Wall thickness, there are only 2 wall thickness, one for the smaller pitched catalyst, one for the larger pitched catalyst. It's purely a matter of strength that the wall is thicker. And they're arranged by dust content. You can see on the right side there, the worst case scenario is coal-fired boilers where you're dealing with a lot of ash and takes a very large pitch. On a pitch base is probably twice as big as the largest of those 2 that I'm passing around. FCCs fall kind of in the middle. You can get away with a 5.0 millimeter hydraulic diameter with FCCs. but that's assuming you've got a very efficient ESP. The important thing to realize here is we do a great deal of flow modeling ahead of time to make sure we've got the right catalyst for the job. The chemistry of NOx reduction is pretty simple when you look at it. The key thing to look at here is the necessity with NO to have oxygen present, which is why we need the eddy flow going into the front edge of the SCR. I'm sure you're all familiar with those calculations. Just picturing what the catalyst surface looks like. You got ammonia and NO coming in, and oxygen coming in, and hydrogen and nitrogen going out. The important thing being that the oxygen has to get to that site to destroy the NO. Otherwise it won't. So the engineering associated with it and the kinetics is extremely important.
Is it a single-step reaction or is it multi-step?
It's single step.
So
Well,
all three reactions.
it's a single step that has really 3 reactions going on at the same time and the catalyst regeneration at the same time. I have an interesting slide for you here in a second that'll show you this. That's it. The reaction kinetics and the reaction mechanism of what's going on was developed by non-U Topsoe, who is Dr. Topsoe's daughter-in-law. I think she's got designs on the top, so she's 63. So she's just about in line for the right age. The important thing to realize here, you've got it's showing here the ammonia coming in on this side, the oxygen coming in on the other side, and the NOx coming in here as NO. The important thing being that the vanadium in the catalyst, without any poisons present, you will never destroy the vanadium peroxide. It will continually plate out, and it will plate out in a pore that is adjacent to the one that it came from, so that you don't end up with any maldistribution of catalyst. So that if you have a clean gas, theoretically, the SCR should last forever.
What if you have SO2?
SO2, then then there's a problem. And not a problem that's unrecoverable. You have to really control the temperature, because the higher the temperature you get, the more SO3 you make, and then you make an ammonium sulfate, which you'll have gypsum in the SCR basically. So it's a control factor. I'll get into that in a second.
What does tungsten do? You show the vanadium cycle. How does
The tungsten is an activator for the vanadium. The vanadium pentoxide is the prime reactant as catalyst. The tungsten's a stabilizer and an activator on the surface. Anyway, John, I don't know if that answers your question or not.
It explains what's happening. It's not. Thank you.
It's the best we can do as far as showing everything that's going on at once. Is there an intermediate? Yes, but it doesn't last very long.
That's fine. That explains it. You know.
The reaction mechanisms, if you look at what you're trying to do here, and the NOx reduction is a fast reaction. You control the film diffusion. This increases with smaller pitch, and high velocity. So you want eddy flow, and you want the smallest pitch or the smallest hydraulic diameter you can afford, given the dust present. So it's not automatic that you would go to did everybody see these? Let's get around. You would think to yourself, well, why not go to the highest pitch possible? And the answer is because the smaller pitches have more porosity and more catalyst per area. So you're trying to go with the lowest pitch possible, and you're trying to get as much velocity through the SCR as possible. The vanadium sites are important from the standpoint that these are the sites that get destroyed when you have poison. And as you get fewer and fewer vanadium sites, the NOx in the stack, as measured, starts going up, and it goes up in a hurry. So what you're trying to do here is protect those sites by controlling the kinetics, the reaction kinetics in the SCR. And the only way to do that is by doing the modeling, arriving at the right temperature, arriving at the right pitch, and making sure you have the eddy flow you need at the front end of the SCR. The SO2 reaction is relatively slow, and that's kinetically controlled also. As the problem is, the better catalyst you have, the more you have to control it, because the more vanadium exposed, the more likely that the O2 molecule is going to get together with an SO2 molecule, and you're going to end up with SO3 and thus ammonium thiosulfate. Excuse me, ammonium sulfate. So it's a balance, like most reactions. The good news is that at the proper temperature, not much SO3 is produced. If you look at this being 100% reactivity, you see the ideal temperatures between 650 and 700 degrees Fahrenheit. You can't always get to that point, but you're achieving above 90%, anywhere between, say, 525 and 750 or 800. Below this temperature, your reaction kinetics is skewed so that you're not converting enough of the NOx. Above 750, and certainly at 900 degrees Fahrenheit, you're going to start having sintering of the catalyst, and you're going to start making an awful lot of ammonium sulfate, because that favors the SO2 reaction to SO3. So what we look for when we first go to a site is, all right, where can we put an SCR where the temperature's right? And then we do the flow modeling to develop the right catalyst. In some tests that we've done with other catalyst manufacturers, and you'll notice we're the only corrugated type here, and that may explain part of the results. We used ourselves as the base case. And the theory here is to show how activity depends on relative SO2 oxidation, and you can see the results yourself. Catalyst B had almost as good a relative SO2 oxidation number as ours, but as you can see, the activity is much lower.
Can you define for me pitch again?
Pitch is the distance between the flat area of, it's the distance across from the peak of the wave to the flat area. Hydraulic diameter is 4 times the area divided by the circumference, so it takes into account the shape of the corrugation.
When you talk about extradate, then are you talking about a honeycomb or something?
Yes.
Like that? Okay.
And your activity in terms of volume percent, is that like say 70% mean that 70% is
70% of the
available to the surface? Or?
Yes, 70% of our case, in that particular case. It's just measuring results, Jim. It's not saying they have less porosity or they have less.
Okay, it's relative to your product.
Yes, it's just measuring the NOx coming out the back end and saying the conversion was 70% of ours.
That's not necessarily a constant metal load or anything
No,
like that.
no. He's just saying in this particular flue with a constant flue gas, with this catalyst at that pitch, at constant temperature, this is the result. Tells us we're on the right track. Deactivation in a clean gas, as I said, is almost negligible. Clean being no ash, no VOCs, no sodium, no metals, etc. Sintering starts happening at high temperatures, certainly above 850 degrees for extended periods, and it depends on vanadium distribution. You get maldistribution in the flue, in the SCR, so that all the vanadium in one area has been either reacted or deactivated. It's the same as if all the vanadium was deactivated. So that's why we shoot for ammonia injection on a basis that is distributed well, and with a static mixer so that we can create an eddy flow all across the SCR rather than certain locations. And sometimes this is hard because you've got a lot of bends and flue lines, and sometimes the ideal place to put the SCR is in a place where by nature you've got maldistribution, and you've got to redesign the flow of the fluid. No pun intended. Plugging happens from dust and ammonium bisulfite, as we talked about. The poisons are the alkaline metals and the heavy metals, sodium, potassium, arsenic, chromium. Even trace amounts will eventually plug all the pores. And this is designed around. That's why we pay particular attention to flow modeling. We're going to look at everything that's in the stream and make sure it lasts as long as you want it to last. If your turnaround schedule is that you're down every 3 years for turnaround anyway, there's no sense making the SCR any bigger than it needs to be to replace it every 3 years. The modules are easily replaceable once they're in. The retrofit is the difficult part. What are we looking for if you come to us, or if you come to anyone in looking for a selective catalytic reduction unit? We want to know what your maximum ammonia slip is, what you can stand, because the judging is for maximum ammonia so that you can have the maximum reaction, but you want minimum slip. So if it's 10 parts per million, that's how we'll design it. Flue gas maldistribution, as we talked about, the composition of the flue gas certainly, the ammonia NOx distribution, how we mix it, pressure drop requirements across the SCR and going out the stack, temperature requirement as we discussed, the ash and organic content, and the catalyst operating life. We've talked about all these a little bit at a time. If you call us in, this is what we're going to ask for first, and then we're going to do the flow modeling. Catalyst type we're going to design. It's going to be a specific pitch, a specific volume, a specific number of layers. It's either going to have soot blowers or not. It'll have a depth that we'll engineer at the required reactor dimensions to fit your flue gas system. Sometimes that's a factor because the ducting might be too thin for the volume of catalyst necessary. We just finished a project for Chevron in El Segundo where we had to make a plenum that was larger than the flue in the duct. And that was a new unit, and it was going into a common duct with another facility. The weight of the catalyst is important. This stuff is not light, as you can tell just by picking up that little piece. Each one of the modules weighs about 700 pounds. So it's heavy stuff. Design life, of course, is very important.
By module, you mean like
2 foot by 2
2
foot.
by 2 foot?
Yes.
So,
References, we've got a lot of them. These are the North American numbers. As you can see all across the board, we've dealt with the most difficult cases, which is coal-fired boilers.
When you say diesel, what are you talking
We've got a bunch of DeNOx units on boats, on diesel engines in plants, chemical plants. Just basically have a stack. They almost look like a muffler. And every boats is a good example. Every boat that lands in California is going to have a DeNOx, an SCR on it.
so when you get out to international waters, they have a bypass. That
Probably. I wouldn't doubt it, Jim.
about? You don't have any in refineries or?
We do now. It's not listed here, but we've put several into Chevron's El Segundo refinery.
Because there's one at the St. Paul, a hydrogen plant that they have.
Right.
I don't know whose technology it
It's Mitsubishi. It's a Mitsubishi SCR. It's our catalyst. So when you say technology, it's who did the system. This is a little bit of a crossover for us. So we're talking about catalyst here, but what we really want to do, what I really want to do, is the whole system in a refinery. So selling the catalyst into it. When you're talking about a hydrogen unit, you're talking about 8 to 10 cubic meters of catalyst. which is a couple $1,000 sale. It's not that big a deal. So I would rather do the whole system. But we're not gonna turn down a catalyst sale either. We have not done any cat crackers in the United States. There are 8 of them, 8 cat crackers that I know of that have SCRs. 7 were provided by Mitsubishi and 1 by Jacobs.
How many in Texas, how many in Houston area?
None.
Yes.
That's a fertile area. Just a list of some of the units we've done. The bottom one is interesting because it's not a retrofit, it's a new unit. We just finished an 85 million standard cubic foot a day hydrogen plant there that included an SCR. And it's a neat one because the addition of the SCR paid out in 2 weeks from a project payout standpoint. Total cost is $1.6 million, and it's running at 1.75 parts per million NOx out the back end, and they have a big payout on NOx credits. That's California. That's probably not going to happen in Texas, but they're real happy. They'll make $9 million every 6 months in NOx credits on that unit. What do we guarantee if you bring us in? DeNOx parts per million out the stack for the life of the unit, ammonia slip, pressure drop, and ammonia consumption. When I say guarantee, we will guarantee it based on liquidated damages. Of course, that's all according to the information supplied by you. And this is our NOx phobia commercial. Try Dr. Topsoe's prescription. There aren't any generic substitutes. And that's it. Thank you for your attention.
Thanks. You've been talking to Jeff Sexton?
No.
No, I don't believe Texas City is certainly the refinery on that refinery.
I have a fellow that works for me that is talking to the folks in Texas City. And they're very interested in the cat cracker aspect. Along, what we've been trying to do, we have not been publicizing this. The work is kind of finding us right now. And except for catalyst sales, in reality, we can only do about 10 of these a year. We're too small to do anything else. So we're gonna be selling a lot of catalyst engineering companies doing these. But my objective is to do about 10 of them in refineries ourselves on a turnkey basis, where we bring a small contractor into the game, or we utilize your on-site alliance partner. Any questions?
Do you measure the NOx coming in and control the ammonia on the stoichiometric ratio, or do you recycle?
No, we control the stoichiometric ratio. So that's why the ammonia slip is important. The control of the ammonia is very, very important, it's very critical. And there's we have a very a sophisticated control mechanism, let's say.
Doing a NOx monitor or something.
Oh, yeah. With feedback. In the California unit, it's very important because they're hardwired into the local air pollution, the city air pollution control. And if they run above 9 parts per million NOx for 15 minutes, it shuts the plant down automatically. So it's pretty critical.
Yep.
Do any of the plants have problems with ammonium nitrate formation, different parts of the system?
No, not that I've ever heard about, Todd.
They don't form any nitrates. Almost all the stuff from the refineries and all, you know.
Right.
Ammonium bisulfate's a problem, but not ammonium.
In terms of a power plant application, you mentioned SIP blowers before. Is it SIP blowing, is there a system to each module that?
It's The soot blowers are the large type, and they're not on each 2-foot square module. They're on each total module. There'll be one in between the modules too. And particularly in lignite coal burning facilities, where you have a lot of ash content, it's absolutely necessary. Because the system would be so big if you designed it for the life you needed, taking into account the ash, that you wouldn't be able to fit it in the flue.
So in a typical utility application, you try to squeeze this thing in somewhere between the ESP and the scrubber.
Right. In a retrofit situation, yes. And I'll be honest, most of the time you've got to move the stack.
Yeah, that's a tight.
Yeah. It's either you don't have enough temperature in the bottom of the stack to put it in there vertically. Typically it's 300 degrees Fahrenheit, and you need more temperature than that. So you're upstream of that, and in old utility boilers, there's just not enough room.
You mentioned earlier, Mike, that there was a reason for the two beds separating. I don't
In a one-bed system, you remove about 70% of the NOx. When they went to the requirement of 90%, people experimented with deeper one-bed systems, and what happened was, as the life of the unit went on, you started to lose the vanadium in the front end of the SCR, and that you don't have the mixture towards the back end. The ideal width is about 2 feet. You get up to about 4 feet, you don't have the eddy in the back of the SCR. So the thought process was, well, let's go to 2-foot modules so that we can put another static mixer in, and we get 90% that way.
You have to inject oxygen between those?
No. There's plenty of oxygen in there. As long as you get the eddy flow, the oxygen's driving the reaction, so that's, you've got an overabundance of air.
You indicated the catalyst depths. Do you actually have different types, or do you, every time you have a new customer, do you design it based on the system?
Every composition is different, and some are like others, and we can give people estimates based on a go-by that we've got with a certain. But it's all the flow modeling doesn't cost very much energy, and it's better to go through it and make sure you've got the right system, because we're guaranteeing it. We have to be sure that we get everything. It only takes a couple of weeks. It's not a big deal.
What about regeneration? Are owners able to take them out every now and then?
Yeah, depends on what the activation mechanism is. If it's one of the heavy metals or sodium, potassium, you can't regenerate.
Like just ash depositions like that?
Ash, you can just clean them. Just clean them and put them back in. If 2 sets of modules, 3-year turnaround, put the new set in, take the old ones out, clean them. The module itself is not that expensive. Compared to other retrofits, this is pretty easy to do. Now, what the economics on the low NOx burners, I don't have it on every type unit, but for example, on a hydrogen unit, going to low NOx burners, the delta cost between that and the so-called not low NOx burners, $200,000 to $300,000 on a 100 million standard cubic foot a day hydrogen unit. Not very much money, and it saves you probably $100,000 in cost per year in ammonia. And it's just more efficient. You just have less ammonia storage, less possibility of ammonia slip. So from an encouragement standpoint, it's worth doing it.
Price of ammonia is skyrocketing right now, isn't it?
Yes, it is. Because of the price of natural gas. The only place, everybody's scurrying trying to build ammonia plants in Trinidad right now because the price of gas in Trinidad is the lowest it is anywhere in the world. And there's an abundance of it. Talking about the difference between a buck a thousand and $9 a thousand. So it's, I don't know what's going to happen with ammonia. Methanol's skyrocketing too, and so is MTBE.
Yeah, MTBE is Hard to get a good price for that.
Well, they better enjoy it while they've got it.
Yeah.
Well, there are some rules that I read the other day that MTBE, there's a big concern about taking 300,000 barrels of refining capacity out of the system and what that will do to the benefits. And I've heard some people start to rethink MTBE.
Well, nobody in the Middle East or Europe is talking about banning MTBE. And if it indeed is banned in the in North America, you've got about 300,000 barrels a day of alkylate has got to take its place.
There's not that much excess
Lot of
capacity
alcohol.
right now.
And that's a lot of alkylate. So it's that's why, frankly,
Next-gen alkylation catalyst is the answer.
well, that's right. That's why we tried to develop the FDA process. But what we found out was it's like any other refinery process. Unless it's a lot cheaper, regardless of the ramifications of the existing processes, whether you're trucking sulfuric up and down the road to regenerate it, or you have HF in the plant, no one's going to retrofit one of those plants. So we looked at it from the standpoint of, all right, let's back off this retrofit idea. Let's not make it an ecological concern anymore. Let's make it an economic concern. So what we're looking at is the new market, not the retrofit market anymore. I think there was a misconception on some of my Danish colleagues.
I don't know if there was a misconception, but certainly, there was a lot of pressure on Mobil's Torrance plant.
Sure. Well, in Corpus, Citgo and Corpus had that leak to June of '98. I got calls the next day from 40 different refiners, including Jim Wick, saying, where are you? Can we? How soon would we get? Can we get one in the field? And that lasted about 6 months. And I'll give Phillips and UOP credit. They've really done a pretty good job of doing what they need to do to at least make a poor situation better as far as HF goes. And I know that MAP has a lot of HF in your system. So it's, let's face it, if it wasn't for the fact that HF was in HF, nobody would be looking for a new process. That is the best process. And we can't, and I'll stand here and tell you that we cannot get cheaper than that. We're cheaper than sulfuric, but we can't touch HF as far as the economics of the process.
That's what we have up in Detroit.
Yeah.
Nobody wants to nobody wants to invest for nothing better than what they have.
That's right, sure. And there's no way to show an economic gain. Yeah. And Diane's down in Phoenix smiling, at Stratco, because right now, for any new plant, she's the only game in town. Nobody's gonna permit a brand new HF unit anywhere in North America. Anything else, guys? Thank you.